one thing I did use CFD for was scale up of crystallizers or batch stir tanks reactors, for instance. So if you look, you would see that, hey, you have particles in there, you need to model them. Another example which you can actually simulate. This example is the fluidized beds, for instance, where you want to simulate. And for this particular project, for instance, the fluidized bed, for instance, it was the project had to do with the disposal of waste explosives. And so with waste explosives, you have to find ways of dealing with it without having to go try, do and die. So this actually did help for us to come up with the safe conditions for them to be able to dispose it of. Anyway, there were other additions as well, even with microfluidic devices. So you want to come up with better mixing in there so that you can actually produce better mixing in there on the micro scale. You could also, others have used CFD for heat exchangers as well. So, well, now I'll just move this whole conversation first to what we know. And you will realize that if you follow the conversation, you would see that most of the stuff you already know is just the way it's utilized. So the CFD approach, which is that when we are looking at the core stages of CFD simulations, you definitely need to have your geometry, whether or not you are dealing with a distillation column or you are dealing with a stir tank reactor, or even if it is your coffee cup, you still need the geometry. So that is your computational domain. And after you have that, you need to have your computational domain is too large for you to be able to solve your governing equations on there. So you need to discretize. So typically you would discretize into whether or not structured or unstructured meshes. So those are basically the approaches. You need to also know the physical properties of your fluids or your system. You have initial conditions as well as boundary conditions. And this is where you then move on to the numerical part. So in the numerical part, you want to find solutions to the governing equations. There are so many ways of doing it. The standard approach that people are taught in general is the finite difference method. You can always start from the Taylor series expansion, and then based on that, you get approximations to the different differentials, derivatives in your equation, and you can actually approximate it. But then the accuracy of your approximation actually lies on what order you actually approach. Now, finite differences are good; they are a good start. But the only thing is they don't work on complex geometries. So people have worked on other approaches like finite elements and then finite volume methods. I'll briefly talk about finite volume methods because finite volume methods is what you would find in ANSYS Fluent and OpenFOAM. And it's actually very natural for chemical engineers to actually appreciate finite volume methods. You have seen it. Now, in terms of post-processing, you have to do something. Now, with the post-processing, you have your results. We will deal with that today. You have your results. You need to actually you need to actually plot, see what is happening in there, and understand the behavior. And if you have to re-solve your equations, fine, then you can do that again. Now, so, well, we know that should be equal to the net efflux, which is the rate of change, the flow in minus flow out plus the generation term. That is it. And now if we take this this as our control volume, you can take any shape at all. If you take this as your control volume, then you can do a balance on it. So if you do that balance, now what then you have is this general differential equation, which here is phi. Now phi could be 1. If it is 1, then you have your mass balance, right? And if you substitute phi, maybe velocity for phi, you have momentum balance. And then if you have specific enthalpy, you have your energy balance. You could do it for species balance as well. So basically, your diffusion terms in this case, which is here, are basically either Fourier's law of heat transfer, Newton's law of viscosity, or Fick's law if you are dealing with mass transfer. So those are the conservation equations that we already know. Now, a little bit about the numerical aspects, which is the finite volume method. So basically, the starting point for the finite volume method is to take the integral of our differential equation. You have it in the differential form. You take the integral over a control volume. So now the next thing is that since we are considering a control volume, we need to split our geometry or domain, our reactor, whatever you want to call it. You need to split it up into smaller chunks so that you can better approximate the solution in there. Now, let's just take a one-dimensional rod, which I have blown up as an example. So as a one-dimensional rod, we've split this as into 1, 2, 3, 4, control volumes, 5 actually. So 1, 2, 3, 4, 5 control volumes. This is just an example. And so we look at the centers, the cell centers. So each control volume is a cell. We call that a cell. And so each cell has a face, which is here. But because it's one-dimensional, you can only see only one part of it. So it has a face, and each cell also has neighbors. I'm bringing these words up so that when we get to the practical aspects in OpenFOAM, you see that these things are not new. So if we have a cell center, cell C, that we are interested in, it has neighbors to the west, which is the west neighbor, which is to the left, and then the neighbor to the east, right? And then each cell is made of faces, and each face is also made of points. So you build your geometry based on the points, and then you have a face, and then you have that control volume, right? We also call the boundaries the patches, right? So excuse me. Hello? Okay. Hello, Dr. Jude. Please, can you mute them? The background. Hello? Okay. So now we have the faces, right? So with this domain, this is just an example. So we have patches as well, which is the boundaries. We call them patches. So this is patch 1, this another patch, this another patch. Now with the discretization, this is a very simple discretization. You could have your discretization, your mesh elements made of quadrilaterals, if it is 2D, or triangular mesh, which is tetrahedrals, if you're in 3D. So you have those patches in there. Now, once you do that, you need to solve this equation, the set of equations that will result from the discretization. But let's move on. Now, with the finite volume method, the integral, so we take the integral of our governing equation. And so once we've done that, we have this term here. Now, we can actually solve this equation, but then an easier way is to basically invoke Gauss's divergence theorem, which is basically saying that we want to know the rate of change of a quantity, maybe the quantity phi in your control volume. If you want to know that, you can basically say whatever the rate of change is equal to the divergence. You look at the flow out minus the flow in, and so you have your divergence theorem right there. So you invoke that, and it's easier to make the integration over this system. So instead of having to compute triple integrals, you basically take differences in terms of the flow at each of the faces. So those differences. So now let's look at just the diffusion and the advection term, for instance, as an example. And for the 1D case, this integral, for instance, results in just the difference between the flow or the flux on the eastern face minus the flux on the southern face. So you multiply that by the surface area, and so you have your term there, that term. So you can do all of that, solve basically approximate all of that, all of the various terms in your differential equation, and you end up with a set of algebraic equations, which you can actually solve. Well, but then because we are dealing with millions, we'll potentially be dealing with millions and millions of a linear system with millions of equations. It's relatively difficult. So we can invoke some of the tools we already know, but iterative schemes like Gauss-Seidel, all of those, whichever multi-grid approaches to be able to solve this equation. So at this point,
hello, Dr. Nyande.
Yes, please.
So please, if I understand this well, this is some form of a conservative equation which exists in the form of a differential equation.
Yes.
Which we have to solve by kind of integrating to the, let's say, the algebraic form. But the integration is being done numerically across an area or a surface.
Yes.
Okay. No, please. Thank you.
Okay. No, maybe let me step back a bit. So what we have is that, for instance, we have to do a balance on each of the cells that we've integrated. So this equation should hold on each cell, right? So what we are going to be doing is that we discretize and we have to solve the equation on each cell. Now, for each cell, you would see that it only interacts with its neighbors, the nearest neighbors. So if it is just a one-dimensional case, then you would have a tridiagonal matrix, which is that you are only interacting with the neighbors, the cells to the east and to the west, if you are dealing with this point P. If you are here, you only deal with this guy and this guy. So it's just a simple balance across each cell. And you have to write this same balance equation for each of the mesh elements you have. And you can already see that this is going to be a very tedious work because of the number of cells you could potentially have. So that's where we are now. Now, there are a few things that I would like to mention, although we did talk about it some time back, which is turbulence. And the reason turbulence is actually important is that we exploit turbulence to enhance mixing, but then it's actually really, really complex to model because on one hand, your energy or whatever kinetic energy you are inputting is on the scale of your geometry, maybe the diameter. It could be maybe some centimeters or even a meter wide. But then this turbulence the energy is being dissipated on a very fine scale, which is on the scale of on the velocity scale, basically. So if you want to resolve everything, you need a really, really fine mesh to be able to do that. And so that is where the challenges come from. So different people came up with different approximations to the turbulence problem. And the most common is the Reynolds averaged Navier-Stokes equation. Another approach is basically, okay, now let's use our mesh as a sieve. So we sieve out whatever we can capture on the mesh, and then anything below is our subgrid scale. So if anything below that mesh size, then we are going to model. Anything on the mesh scale, we are going to solve for. So that is basically the large eddy simulation. But the most accurate approach is basically to solve the Navier-Stokes equations directly using the direct numerical simulations. But this actually requires substantial work, computational cost. So typically for most of the engineering applications, we typically consider the Reynolds average Navier-Stokes equations. Now, with this, we would end this small, short introduction and then move on to the business of the day, which is to now look at the applications aspect, which is really getting our hands dirty and doing the OpenFOAM aspects. So with this, I would ask that if you have your computer in front of you, then let's just proceed with that. So with the OpenFOAM aspect, I'll give you a short overview of its capabilities and some of the things. It's not even an exhaustive list, but then whatever may be your problem, or the problem you are dealing with, you most likely will have something there for you to be able to help you solve those engineering problems. So OpenFOAM capabilities include heat transfer. You can solve compressible and incompressible flows. You can do combustion and chemical reactions, multi-phase flows, mass transfer. You can do particles. Even there are even options for finance. We would go into the directory structure, and you'll see that even if you are interested in finance, you can even solve some of those problems there. So those are the steps. Now, with the physical models that are available, we would basically consider turbulence models, which is the Reynolds average Navier-Stokes equations, the large eddy simulations. There are also models for your rheology, because not all fluids are Newtonian. So for non-Newtonian fluids, there have to be different viscosity models for them. And then thermophysical models as well. You have equations for different momentum transfers if you are dealing with multi-phase flows. And so porous media, if you are dealing with catalysis and all that, phase change, you can handle all of those models in OpenFOAM. Now the method, OpenFOAM is actually based on finite volume method. It's a finite volume method solver. You could have structured or unstructured mesh. And for the mesh, for instance, I did show that we had the very regular mesh, and then you have the tetrahedrons, which is unstructured. So you can actually handle different kinds of meshes in there. You can have steady state or transient simulations as well. And so there are different algorithms to actually handle the pressure, the continuity equation and the momentum equation. So one challenge in incompressible flows is that for incompressible flows, we do not have an equation for pressure. So we have 3 equations for velocity, no equation for pressure. So we need to find a way to actually account for pressure in there. So there are algorithms in there, either the simple or piezo algorithm. And so there are two mesh generation tools available, which is your block mesh for structured meshes, really nice. That's what we will deal with today. And then tomorrow we will deal with the unstructured mesh. So you have mesh manipulation capabilities. Let's say you have a mesh that is generated in maybe Fluent, for instance. Would you be able to use those meshes? Yes, you can convert those meshes to OpenFOAM and use it. Only thing is, in fact, OpenFOAM's meshes are all 3-dimensional. It has to be finite volume meshes. So that's one thing you have to consider. Now, if you have your computer in front of you, I want you to source OpenFOAM, and then we can do some, begin with the hands-on session. So to source OpenFOAM, anytime you start OpenFOAM, you need to source it, which is that it has to load the various directories in the configuration files for you to be able to work with OpenFOAM. So to source OpenFOAM, just type in your terminal, source WM project directory, which is your installation directory, etc bash rc. Just do that, and then we can continue. I've already sourced OpenFOAM, so
Sorry, Dr. Baggie.
yes.
People are saying you should repeat how to solve.
How to solve what?
No, how to solve.
Oh, okay. Oh, okay. Yeah, I'm coming. Let me just share my screen. Can you see my entire screen?
Yeah.
Okay. Okay, so this is how you source OpenFOAM. So just type source here. Can you see? Hello?
All right. So you say you type source.
Yes, source, and then the dollar sign, WM project.
WM. Is there a space? Yes.
So this.
So please,
Have you
could
been
you
able to source
maximize
it?
your screen? Hello, Dr. Baggie.
Yes, please.
Please, could you share the file you're using with us? Because I find it
The what?
difficult to see the entries.
Oh, okay. Okay, hold on.
Maybe
Can you
comment
see?
sections.
Can you see?
Okay, this is fine.
Okay.
Dr. Andy,
Yes.
why are we not just sourcing it by editing the bash RC file? Is there a reason why you would prefer
No,
sourcing
okay,
it at
well,
every setup?
well, you can do that as well. You can do it directly if you want to.
Does it
If
have
it's
any
already,
effect on does it have
you
any
don't?
effect on your application if
No,
you source it? Okay, all right, thank you.
no, no. So basically, well, because a lot of people are not familiar with Linux. So anyway, so you can just source it directly. If it is already sourced, we can proceed. Are you done?
Guys, are you able to source? We've already sourced it. I think that's yeah, that's what you're going to do in that file. When you go and change the reading.
Let me see if I can just share. So you can just copy and paste this in your terminal, and that should do. Dr. Jude? Dr. Jude Bonsu. Is anyone successful?
Hello.
Yes, Dr. Jude Bonsu.
I think, yeah.
Okay.
At least the people and the PD lab are successful.
Okay. So can anyone share their screen? Anyway, so while you can just copy and paste. While you do that, we can just proceed with this until people are ready, and then we continue with the hands-on session. Anyway, so OpenFOAM actually has a number of, all applications are basically considered either solvers or utilities. Okay, so hello. Yeah, so the solvers are basically what you, it handles the numerical aspects of the solution. So basically the governing equations that we just talked about, the solvers are responsible for providing a solution. The utilities actually help you either manipulate the data before you actually solve. Hello?
Yeah.
Hello.
Hello?
I can't hear anything.
Yes, because I was waiting to get feedback from you. So have you been able to source OpenFOAM?
Yeah, I'm just working on it.
Okay.
Yes.
Okay, then we can proceed. So, okay, so with this, I'll just proceed with the directory structure of an OpenFOAM case file. So typically the directory structure looks this way, which is that you have the case name, you have the zero directory or the zero folder, the constant directory, and then the system directory. Now, the zero directory is basically the place where you put your initial conditions. So your pressure and velocity, for instance, would go into their various files or dictionaries. And then in the constant, that's where you have your mesh. And then your transport properties like viscosity, everything has to be defined. We'll do it, an example, a few examples, and you see it. And then from there, we have the system directory, which contains the control dictionary where you actually basically control the numerical aspects of it. And then you have the numerical schemes, various discretization schemes and solution strategies in the FV schemes and FV solutions. Now, once you start obtaining solutions, you see that there'll be other time directories. Maybe you want to get your solution at every maybe 0.1 second interval. So you would see solution directories named with respect to time. So let's just do an example here. So the example here would be the lead-driven cavity flow. So with this example, we basically have a tank with air in it. For instance, it could be water, and on the top you are moving the lead, and so you want to simulate to see the flow behavior in there. So our problem is incompressible laminar flow. Our Reynolds number is going to be 100, relatively low, and then we are going to deal with 2D, but you can easily extend it to 3D. We need to generate the mesh. We set the boundary conditions, initial conditions, and all that. But here, note that these walls have a no-slip boundary conditions imposed. So let's just proceed and see. So this is basically the workflow. You would have to, initially you would run it blind. We'll basically copy and move it to some directory, run block mesh, which is your mesh generating tool. We run icofoam, and then we post-process with parafoam or paraview. And then we can actually see the solution. And then after that, we'll go into details and look into the various directories and what we have in there. And then I'll explain everything. And then we'll run other examples as well. Okay, so here, let me just, I go CD. I want to make sure I'm home. And then I list. So, well, I'm basically listing. And so you can see I have here CFD tutorials, basically different directories that I already had in place. So I'm just going to move into OpenFOAM. So you can just type shortcut foam, and that takes you to OpenFOAM. And here, okay, we have various OpenFOAM directories. That is how OpenFOAM is organized. So if you want to see it in a tree-like structure, you can just type tree with a flag, capital L, and how many levels? Maybe 1. And so you would see it displayed accordingly. So here we have the applications, which contains all the utilities and the solvers in there. We have the tutorials, which we are going to be copying from. And we can make a directory here. So let's just proceed and make a directory if we want. So let's make a directory, which is mkdir. What do you want to call it? Okay, let's just call it CFD course tutorial. Okay. So we have CFD course tutorial. Let's move in. So we are here. Now, we could go to the tutorial and then copy. So, well, since we are here, home CFD course tutorial, I can also change directory and just type tut. So there are, okay. There are various tutorials in here. Excuse me, are you following?
No, you're too quick.
Okay, so hold on. So just type tut, make a directory, which is mkdir, and then name it whatever name you want to give it. So you can just start from here. Just type in tut, which is an alias for tutorial. Let me know when you are ready so we can proceed. Oh, okay.
Please, can you go further up?
Hello.
Okay. Yeah.
Please, the command tree dash L1. We have a problem with that.
Okay, so it's fine. We can still proceed without it. We can proceed without the tree. So you can install it. Basically, just type in sudo apt get. I'm sure tree should help you install it directly. That's if you're connected to the internet. We can proceed without a tree.
Okay, I think we can move on. We installed it.
Okay. Okay, so now that we are on the same page, our tutorial, since we are dealing with incompressible flow, we need to go into incompressible. So we need to change directory to incompressible. And then I'm listing it here. So you can see we have various solvers in there under incompressible. They are named according to their solver. So we have IcoFoam, we have adjoint shape optimization, all of those details. So we are going to be dealing with IcoFoam. So change directory again to IcoFoam. And then we look at what we have. So under IcoFoam, we have the cavity and then an elbow. So we are going to go into the cavity. We can try the elbow later, which is the Pitt's daily example. We'll do that later. So let's just go to cavity. And so we have cavity clipped, cavity clipped, and then the cavity grade. So we move to, we are going to be copying cavity.
Hello, Dr. Baggie. They are saying wait for some 5 minutes. They just now type the cavity.
Okay, okay. And while we are still here, you can see the various cases you can run. So those interested in the solids mechanics, for instance, so you can look at the stresses around buildings or bridges and all that. You can simulate all of those examples. You can look at finance, electromagnetics, and even other discrete methods as well. And in the basic, if you need to solve a differential equation, a partial differential equation, you can actually go into basic, you find it there, and you can basically solve the differential equations in there. But we would explore those directories in a bit.
Doc, please, we can move on.
Okay, so basically this is the game plan. We would go in there, we'll copy from here, and then we'll paste it into the new directory that you created. For my case, my directory is called, hold on, CFD tutorial. So I'm just going to copy that to home. CFD course tutorial. And I'm going to call it, well, same cavity, so it's fine. I'm not going to change the name. So now let me change directory to home. So I have it there. Are you with me? We're here. So step 2 is basically copy that. Once you are done, you change directory, you go in there because we are going to be working in that directory, your new directory. It is always a good idea to clean whatever case you've copied. So you clean by basically saying clean tutorial, foam clean tutorial. Foam clean tutorials. So that helps you clean your tutorial before you even start working on it. So my case is clean. Are we all on the same page?
Hello, Doc.
Yes.
With the CPR entry, I don't know what you're doing there.
So here, right?
Yes. Yes.
So I'm copying.
Oh, okay.
Hello? I said copy recursively the cavity case. You go into this directory and copy the cavity case, and then there is space in between that, and that is I'm returning to my home, and within my home directory there is the CFD course tutorial in that directory. So copy into that directory. So remember the document Martin shared with you. If you are copying, you copy, and then from to the source and then to your destination. So that's basically what we are doing.
Okay. Okay. But I think we are getting invalid option, something like that. Try CP help for more information.
Can you share what the error message is? So if your directory is named differently from mine, then you should use the name of that directory in which you are interested in working.
Yeah, I did that, but because I saved it as CFD.
If you are ready, let's proceed. So now we can just run block mesh to generate our mesh. So type block mesh to generate the mesh. We can check the mesh with check mesh. And so you would see that everything, the various criteria, which is the openness, the orthogonality, and then the skewness are all okay. So we can proceed. But before that, let's type paraphone to see the mesh generated. So I have paraphone opened and I can press open. Okay, here, surface with edges. So this is the mesh. It's quite coarse, as you can see.
Doc, I don't know if you could hold on a bit.
Okay, no problem. So we are still here. So after this, all you have to do is type in block mesh. Can we proceed?
Yes, please.
Okay, so are you in paraphone? Do you have paraphone open? Here.
Yes.
Okay, so click on the apply and then go to this and surfaces with edge. Now you can change, you can play with it, look around if you want. You can have your surface and you can change stuff. even here. So here you have the various parts of your mesh, which is we have some fixed wall. If you want to see which part is which part, you can actually just click things out
Doc,
there. Yeah.
you go over the paraphone part.
Okay. So you want the command. Is that what you mean? Hello? Hello? So just type in parafoam. The para part is all small, and then you have the capital foam. And so that should open para view for you, and you just apply. You can see the green button, apply. Here. So apply. Do you see it? I'll share these slides with you so that you can play, test your hands on it. So if you notice, you will see that our mesh is 20 by 20, 20 in the X direction, 20 in the Y direction, and only one in the Z direction. Can you see it? So the mesh is 1, 2, 3, 20 by 20. If we are done, you can close, and then we are back here. So now let's run icofoam. Are you ready? Are you ready?
Yes, please.
Hello?
I can see. Hello.
Where are you? Where have you gotten to? What?
The current
Do you have the solution?
Not yet. Just hold on a bit.
Okay, can you share, at least share a screen so I can see where you are? So I'm closing this. And so we are here. Now, I want us to see something because there are a number of issues or errors that would occur if nobody is around and you are doing CFD simulations. So let's just first of all try something. Now let's increase the mesh resolution from, so I'm going to just type 3 here. Okay. One. Okay. So I'm here. I'm going to clean this case file. So foam clean tutorial. Are we all on the same page? So it's clean. I'm going to go into system directory. And then go into my control deck and make certain changes. So my editor here is the nano. I'm going to be using the nano editor. You can use maybe gedit or whatever you want, but I'm using nano in this. CD system nano. So this is what I am seeing. So here the block. So let me just use this to explain what the block mesh file looks like. So you have convert to meters. So whatever dimensions you have, you are going to be scaling that by 0.1. Everything is going to be multiplied by 0.1. So that is your scale. And so because it's just one big block, you need 8 vertices. So you start numbering from 0, 0.01, 2, 3, 4, 5, 6, 7. Now you need to, after that, so you have your vertices, you need to use those vertices to form a block. And so you start with the hex. That shows that it's a hexahedral, right? And so you start with 0. It has to, the ordering matters, which is that the number should form a right-handed system. Hello? So this tells you your block, right? The various vertices.
Hello, Dr. Baggie.
Yes.
Hello, Dr. Baggie.
Hello?
Please, I think someone, the block mesh.
Yes.
It's working, but it looks a little bit different.
Okay, can you share it, what you can see?
Okay, sharing. Turn your mic off. So this what is showing.
Okay, yes. It's the same thing.
Okay.
Okay, just move down. So we can use yours to explain. So basically, you have your file format, which is ASCII, and then it's a class. So this is object-oriented programming, C++. OpenFOAM is a C++ code, actually. And so your object is the block mesh dictionary. Now you are converting, you are multiplying everything, all the dimensions here by 0.1. Right? So you are multiplying by 0.1. And then now your vertices, which are your points. So when you start working or trying to make your own case file, you need at least 8 points, 8 vertices to be able to form a block. So now from the vertices, you move on to the blocks. And so you have this hex telling us it is made of 8 sides or so, right? And so if you have this, so you have to then start from the numbering. So the first vertex is 0. The second one is 1, 2, 3, and all that. So you have a hexahedral block with 0, 1, 2, up to 7. And this 20, 20, 21 is telling you the number in which the number of control volumes that you are dividing your block into. So if you remember, when we look at parafoam, we saw, I asked you to count. In the X direction, in the Y direction, you have 20 cells each. And then in the Z direction, you have only 1. This tells you you are already going to be dealing with a 2D case. So only 2-dimensional, not 3-dimensional. Now I want you to change this 20 to 200, 200 each. Just press down, arrow down, and then, oh yeah, 200, 200 each, and keep that one there. And then Control X. Yes, type Y. Y. No, okay, just save and exit. Enter. Enter. Okay. Now, type in block mesh. Not block mesh depth. Yeah, block mesh. Enter. Oh, you are still in system. So anytime you see this error, it means you are in the wrong directory. So change directory, CD, and then move back. No, not Siri. CD dot. And then now block mesh. You can just arrow up key. Arrow up key should take you back. Okay. I see. So now icofoam. First of all, before you even go, okay, well, that should work. Have you noticed that it's relatively slow? It should diverge, yes. Now, the only thing you've changed is the discretization, but then your solution has failed. And so those are the beginnings of CFD. typically when you try this, one thing, the indicator here that you are going to diverge is that your current number is very big. It's greater than 1. So now you don't want to change, you want a fine mesh, right? And so you want to decrease this current number. The current number basically tells you that you are propagating information too fast. The current number is basically the ratio, is the time step size delta t over delta x. So if that exceeds 1, so there is a constant there multiplying delta t over delta x. Now you've made your delta x very small by increasing the number of mesh points. So you need to make sure that your current number, your step size, your time step size matches the same condition. So now go back and then go to your system. Go to your system directory. And then no, not block mesh, not block mesh. Go into your control dict. And now change your delta t, which is the time step. You can see we have various applications. So change your delta t, put 0.00 in front. Maybe you can even put 3 zeros. Yes. Yes. 0, 0, 0. Another 2 zeros. Put 2 more zeros. And then increase your end time to 2.5. The end time doesn't matter. It's your delta t that counts. Okay. And now exit, Control X. So this tells you control plus whatever you can do. The command, yeah, Y, and then enter. Now exit, go back one step, CD ... And then now run IcoFoam. No, IcoFoam, your mesh hasn't changed. Okay.
It's giving us an error.
Okay, let's go back to the control dict and see. I see.
We've opened it.
Yes, go up and let's see the header bar. Move up, arrow up key. Let me see. Delete
No, please,
location.
what does IcoFoam do?
What does IcoFoam do? IcoFoam is your
Yes. What does
IcoFoam is your solver. So
okay,
it's one of the
so
solvers.
for mine, Elvis, I had to use a simple foam.
Yes. So IcoFoam is the application, the solver, and then
so for mine, I don't have to use.
No, in your case, you have to use simple foam.
You said simple form is the application, and then IcoFoam is the solver.
No. So simple foam is a different type of solver. IcoFoam is basically a different type as well. So there are differences in that. Simple foam is a steady state solver. So you are not considering time dependence.
Okay.
ASCII. Hold on, let's see.
So meaning for IcoFoam, we just manipulate the time.
Not only the time. Actually, you can change a lot of. You mean for control dict? What do you mean? What's your question again?
I'm saying that for IcoFoam, we are solving the parameters that we only control the delta t, or that's the most important.
Well, that is not. Well, that is the most important in this case. But then you can change anything there. If for instance you have an issue or you don't know what to change, maybe you are starting from start time 0 and you don't know what other options, you can just put your name there, or you can put banana and it should tell you the options. I tried to find this, I couldn't find it, so these are the options you are allowed to. So you can do that. We were going to get there, but it's a very good question.
Okay.
Yeah, so exit this because I can't
that different
see.
from ParaView?
ParaView is your post-processor.
Or in ParaView, I can still change the entries like delta t over there. Or
No. So once you get into
everything must be done
ParaView, you
here.
are only going to look at solutions. Whatever you've solved, that's what you are going to be checking.
Okay.
Yeah. Anyway, so exit because I can't see any issues with this this file. So Control X. Okay. And then IcoFoam again. Okay, CD dot, no, CD first. Space dot. And then type in IcoFoam and let's see. Enter. Let's see. Problem while reading. At line 1. Control dict line 1. Okay, you're pointing. Let me try it first in this case, and then let's see what happens here. So let me just project my case and we can see.
Okay, please.
All right, no problem. Let's see if we are facing a similar issue, because in CFD you are supposed to face issues. Well, you would face issues if you are not running a tutorial, so you need to be able to troubleshoot or see where those issues are coming from. So at this point, I'm just going to run ICOFOAM again, and let's see. So you can already see my current number. It should diverge soon. Good. So this has diverged, and you can see current number, mean current number is 770, which is way too large, way bigger than 1. And so
yeah, this is what we have.
So this is where we were. So I'm just going to now go to system, ls, and then go to nano control dict. And so here I have ICOFOAM. I haven't changed anything up here. ICOFOAM, form file ICOFOAM, that time, end time. Okay, I'm just going to increase this to 2.5. And then my delta t, my time step, which is what I'm trying to correct for 0, 0. Okay, 0. And so Control X, save yes, and enter. And now I need to change directory. ICOFOAM. So my case seems to be running just fine. So project yours and let's see. And you can see that this is taking a very long time. Let's see your case file again. Share your screen.
Okay, please.
Share your screen.
Yeah, please, I'm sharing my screen.
Okay, so let's go back to your control dict. There has to be an issue there. I think line 1 has an issue. No. Okay, line 1. Let me see. ASCII. Okay.
I think you used 4 zeros after the decimal points for yours.
I'm not sure, but okay. I don't think that's where the issue is coming from. Move all the way down, scroll all the way down, and let's see. Okay, so just use 4 zeros and let's see.
Okay, please.
Okay. Yes, why? Move back 1 step, CD. Yep, and then now ICOFOAM. You know what? This is not very informative. Wait time. We could go there, but then were you able to run the first case? Let's just get there without modifying anything.
Yes, please.
Okay. So in this case, go back and copy the case all over again. So remove the whole directory, remove the files in there, and then copy the tutorial again, and then we can modify.
RMR, right?
RMR.
Okay. Is it a system direction?
No, well, you can go back and remove the whole cavity case and then copy again. So just go back to tut. This, hold on. I shared this. So copy, and then we come back and modify. My case is still running, so you can. Have you been able to copy? Do you remember how to copy?
Yes, please. CP.
Yes.
Please, I'm confused. You said we should remove the whole cavity.
So yeah, so go back one step.
Okay.
CD dot and then RM and then no yeah cavity, yes. Try it and let's see. LS and let's see. So the cavity case is gone. Now go to the tutorial. Just type tut, TUT. TUT. No, small t. TUT. Small TUT. Small letter T. Yeah. And then LS. Incompressible. CD incompressible. LS. You always want to see what is in there, and then you can copy.
Sure.
So we are dealing with IcoFoam here. So try IcoFoam. CD, go to the directory with IcoFoam. See what is in there. Yeah, CD. Do you know what is in there? Well, let's see. So you can copy. Yeah, so copy. Copy.
Please, I can't hear what you said.
I said copy. So CP. So you need to copy the cavity case. Yes. Yes, copy. Yeah, the whole. Yeah, that's it. Space. Put a space there. Yeah, and then now where do you want to take it? Which directory? No. Now, what directory were you working in? You were working in home CFD course tutorial. So that's where you want to put it. No, see, go up there. You can see the tilde/CFD. That's what you have, CFD course tutorial. Tilde. Yes, yeah. So that's where you want to put it. Enter. And now you can go back to your home. just CD and then tilde, space tilde, and then ls. Or you can just change directory directly. Do you see it? Yeah. ls. Okay, now you have it. Go in there and let's see what you have. So go to cavity, CD, cavity, change directory, cavity. Okay, now first try to run this case, block mesh. Type in block mesh. Type in block mesh. Enter. And then IcoFoam. That works. Okay, so we know it works, right? So one thing you could do is you could create another copy of that. So just go back one step and CD, go back, CD, that dot, and then now CP, R, because you are copying a directory, flag R, yeah, space, cavity, and then rename it, slash, and then final. No. Forward slash final. Yeah, you had it. Forward slash final. No. Space. Go back.
You said cavity,
and then now basically you are in the cavity, right? So take out the slash. Go back, take out the slash. And then space, cavity now. Type cavity again. No, before your final.
Yeah. After
slash,
cavity.
yes, slash, forward slash, and then cavity fine. So you are renaming whatever you are copying in the same directory, but you are calling it fine, or you are giving it a new name so that you can modify that one, and then we see what happens.
Okay.
Yeah. Even final works, so that is okay. Enter. Okay, so I see. Remove that one. Remove the cavity forward slash. And then enter. Okay, so ls.
That's final.
Yes, you have your final. So go into final and make the changes. Go into block mesh and 200, 200. No, you need to go into the system directory first. No. You need to go all the way into the system directory. No, block mesh dict. The dictionary is different from the application. Enter. Okay, so now make the number 200, 200 at hex. Enter. Okay. Now generate your block mesh. No, generate your mesh first. You need to generate the mesh. Okay. And then it's not going to work, but try it out first. Yeah, enter.
I can now type the icon.
Yes. So you can see your case is diverging. Do you see it? You can see that the current number keeps increasing after each iteration.
Yes, please.
Okay, so now go to your system directory and change the time step. Make the time step size smaller. I think you should increase the end time to 2.5. That is fine. And then 3 zeros. One more.
3 zeros rather.
Yes, I had 3 zeros, so that is fine. 2 zeros could work, but let's just try 3 zeros. No, sorry. No, go back. It's not going to work, but try it again. It's fine. Let's see. So this case works. It appears this is working. So I don't know what happened initially. Let me know if anything changes. If it doesn't work, you can always decrease the step size, the time step size. So, yeah. So this has actually demonstrated some of the issues you could face when you even run a simple case, that you've changed something somewhere and then you violated something else somewhere, which is when you made the time steps, the mesh size smaller, you've basically caused divergence. This should diverge again, so you can deal with it. It's diverging soon. Yeah. So
Doc, it's still diverging.
Yes. So increase the number of zeros. Add 2 more zeros to the time steps. Yeah. Two more zeros. Yeah. Yeah. And you can see this time it should work. So this is just an example of some of the issues you could probably face over there when you start dealing with OpenFOAM. So it's good to actually understand this outputs that you can see out there. Most of the time, your current number is very important. You need to know that. So with this, I'm just going to give you an assignment, which is that you try to run the case for the Pitts Daily case, the elbow case. So copy. This is for everyone, not only him. Hello?
Yes, please, you are listening.
Okay, so you copy. This is, let me just put it there. So the game plan is to copy the
Please, should I
PITS
stop sharing my
daily.
screen?
No, okay. The PITS daily case is the elbow case, sorry. So I've sent it as part of the Zoom link. Can you see?
Yes, please.
Yes. So the elbow case is where you should try your hands on. Anyway, so if it is taking too long, you can kill it.
Please, you said?
If it is taking too long, you can kill it. You can end it, and then, or you can play around with something that works. 2.5 seconds might be too long for your computer. So
we can decrease.
Yeah.
We can decrease the end time.
You can, yes, you can decrease the end time. That's one thing you would notice. So now I want to actually use this to actually wrap up some of the things we've talked about earlier, which is I want to connect you to whatever I've discussed earlier. So let it run, and then let's go back to the theory parts. Okay.
Yes, please.
All right.
Hello,
So
Dr. Baggie.
here, yes, please. Yeah.
This is Martin. So
Oh,
please,
Martin.
yes, so far we've most people have been able to at least go through the first
Tutorial.
two tutorials, right? Yes,
Okay, that's great.
I think maybe the time step one, people might have to watch a recap, and we are recording, so people might have to watch that again. But at least the first one. So I think what we've gotten so much of the steps, right?
Okay.
Copying this, mostly the Linux, like navigating through the Linux and then
Yeah.
getting the files. But right now, we would like to understand the functionalities of the various things we use, like so is PowerFoam the viewer, like what we used to view when
Yes, PowerFoam is your viewer. That's what you basically use to view your cases, and that's where your results will be. So you look at your mesh in there, you look at your geometry in PowerFoam. So anything you need to look at that has 3D and your solutions as well, you can find them in PowerFoam. So you can spend some time there just playing around in PowerFoam.
Okay.
Now,
Okay. So I'm thinking.
Okay. The next
I'm
thing,
thinking
the
so
next,
far. Okay. Sorry. Please go on.
okay. The next thing is that you have used block mesh, right? So you've used block mesh. So this is what we have in the pre-processing step. You have to generate your own geometry. You generated your own geometry in block mesh, but sometimes you may have to use STL files. Hold on. So you generated your geometry in block mesh, but you may have to do it with SEL. So block mesh is basically your pre-processing mesh generation tool, and then you actually meshed it. Now your solver, the solver we used today is IcoFoam. Someone else used Simple Foam. IcoFoam is just for non-steady state, time-dependent is a time-dependent solver. Simple foam is a steady state solver. Do you get it? And your
Yes.
post-processing, we did it
So,
in.
please, are there more solvers?
No. So I'll show you examples of the solvers you have. So your post-processing you did in Parafoam or ParaView. That's where you did your post-processing. Now, so the solvers are here. Let me see. So example solvers are here. So incompressible solvers are given here. You have the pimple foam, piezo foam, shallow whatever foam, icofoam. Those are the solvers. You get it?
Okay.
So if you want to know what solvers you have, I'm just going to kill this. If you can see my screen, you can see it running. So I'm going to press Control and C to end it. So I don't have results now. I'm just going to type solve. And so I'm in the solvers. You see? Can you see my screen?
Yes, please.
So these are the solvers in OpenFOAM. So they are all here. So you have the DNS, combustion, and all of that. So if you go into each case, for instance, you are dealing with incompressible. So
It's the networking.
and so you can see the solvers here for incompressible flow. So those are the solvers you can use. Do you get it? Martin.
Doc,
Martin.
can you please just the step just before this? Can you please go over that?
Okay,
The bandwidth.
so here. Okay. So first you type in solve. That is a shortcut for solver. It's alias for solver. So
But in the
SOL.
incompressible folder.
It doesn't matter where you are. If you type in
Okay.
SOL, it takes you to the solver. So just type that. So if I type in solve, for instance, it takes me back to the solvers. Do you see? Hello? Anyway, so it takes you to the solvers. And so there are solvers for each case. So for solvers for each particular case that you are dealing with. So you would see that if you are dealing with a heat transfer case, let's go to heat transfer.
Yeah, on the same page. So
Do you see
CD.
it?
Yes, please. CD heat transfer.
So for heat transfer, you have a different kind of solver. Do you get it?
Yes, please.
So those are the solvers. There you can actually develop your own solver. And you can call it Martin. What? Hello?
No, Doc, we are following.
Yeah, so you can develop your own solver, which was supposed to be our final case, and you could probably call it Martin foam, so that when you want to solve any case that is of interest to you, you could use Martin foam to solve your case.
Okay.
Yeah, something like that. So it's just C++ code.
Okay, so does it mean most of what we were doing earlier was trying to access tutorials that were
Existing
already
solvers.
existing tutorials and then
Yes.
running them?
Yes, so you just run existing tutorials, and the case with, so this case was just to investigate the performance. So you will just run everything blind.
Okay.
Yeah.
So does it mean that when we ran block mesh, the geometry had already been created? So we were just kind of calling it.
Yes. So basically, when you look through, I think this is something. That is a very important question. Let's go back to home, and I'll show you the cases, for instance.
CD trend space trend. I'm looking at the screen.
Here.
Then looking.
So I'm back to the tutorial case, right? So initially,
I've increased the brightness. Can you see now? Trend. So it has worked, but I didn't see what it did. Doc, please, can you go back just before the tree?
oh, okay,
After we went
this.
home.
So you can always just say CD and this,
Yes. Okay.
yeah, and then you move in to your home. So try to read the document, the PDF file I sent you, and practice on it with those examples. You can create your own thing and just practice.
Okay, so we managed to go home, but we see
Okay.
we run some tree or.
Oh, well, you can always do that. You can always look at the.
Okay. Okay. I haven't done it.
So when you first start, you need the zero, the constant, and the system directory. We can actually create one on our own. All right. So let's go
Dr.
to
Baggie,
Martin. Who was that?
please, please, I'm called Chrysler.
Oh, Chrysler.
Please,
Okay.
I was asking, after you went home, that's where
Yes.
that's where I lost you.
Okay. So after I went home, so you can just go to the directory in which you want to go directly if you actually know the path. So oh, this is so long. So here,
Please, I can't hear what you're saying.
hold on. So if you know your path, this is what I did, right? I knew the path in which I was, right? So I just changed directly that and then went there. Here. Do you see it? Can you see?
Yes, please.
So you can do that. If you know where your things are located, you can just CD and go directly to that place. Are you following?
Yes, please.
Okay, so once you are in there, I want you to clean everything you have in there. Just foam clean tutorials, and you should be able to see it that everything is gone.
Please, I'm on.
Have you been able to clean the tutorials? So you should.
I went to edit. It's still there.
Share your screen.
Yes, please.
Okay.
Please, I'm sharing my screen.
Okay. So foam clean tutorials. Yes. Tutorials. You're not done. Okay. And let me see. Okay, so you have zero constant. Okay, well, final system. I don't know what the final is, but that is fine. So now to set this up, all right, in most of the cases, this is what you need to start with. This is the bare minimum you need to start with. The zero directory, the constant directory, and the system directory. So that is what you do. Now, if you move into the zero directory, for instance, there are some files in there. So you can just go to CD 0. And then you can see that you have the initial conditions for your velocity and your pressure. So each case you are going to be setting in OpenFOAM. So you need to have that. So if you are solving for a heat transfer case, for instance, you need a velocity, you need a pressure, and you need one file for temperature. So you can type in nano and U, nano U, and let's see. So you can see this is what the U file looks like, the velocity file. So it defines the initial and boundary conditions. The initial conditions is that initially the internal field, the velocity is all 0 within your domain, right? And you can see also the dimensions. The dimensions 0, 1, -1 has meaning. And basically the first one is mass. It tells you that you don't have anything multiplied by mass here. So the mass term is 0. So kilogram is 0. And then you have length, time. So you have meters per second here. Do you see it? Those are the powers of each of those dimensions. So kilogram, length in meters, time in seconds. Then you have mole. So the dimensions. You have mole, you have addition. Oh, we have that. I'll show you tomorrow. Anyway, then you have your initial conditions, which is the internal field. You are saying it's uniform. If you don't know this, put banana or put your name, and it's probably going to give you an error, but give you what you can have over there. Okay, and then your boundary fields are basically the patches. So you have the names of the walls, which is you have a moving wall, you have some fixed walls, and then the boundary condition, you are applying no slip boundary condition here. So each case has to have all of those. And then the front and back is empty. So you are basically solving a 2D case. As you remember that we only had in the Z direction, we only had one cell. So you are only solving a 2D case. Anytime you have a patch of type empty, it means you are solving a 2-dimensional case. You are not considering that particular boundary. Do you get it?
Yes, please.
But there is something also you need to consider up there, really important. Go up. All the way to the top of the file. Okay, now pay attention to the object, the class. You are dealing with volumetric vector field. This means that your velocity vector, it is a vector, right? And then it is throughout the whole domain. Now exit this and let's look at pressure and compare. Also pay attention to the dimensions as well. So exit, Control X. No, just nano. Nano P. So it's a file, so you need to read with an editor. So P, enter. Enter. So you can see this is a scalar. Pressure is a scalar field. Do you see the difference? Do you see it?
Yes, please.
And then the dimensions, you can also see that the dimensions are basically meter squared per second squared.
Yes,
because
please.
you've divided by density. Everything has been divided by density. That is why you don't have units of mass in there. And then because pressure is a scalar, you only have 0. It's not a vector. It's just a scalar, one value. It's not 0, 0, 0. So pay attention to that. And then you have the 0 gradient. Pressure gradient, you are saying it's 0. And then your fixed walls are also 0 gradient. And you also have the type empty. So you can copy this if you are dealing with temperature. If you want to consider temperature, for instance, you can also add temperature. You can create a new file. So go back. Let me show you how to do that. Exit. Control X. And then CP, 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 and then P, copy temperature, copy pressure, because you want to change it to temperature. So do that. CP, and then P. You are copying the pressure file. And then now you want to name it, no, T, capital T. Yes. Enter. And let's see. Now LS. So you now have T, U, and P. Now go to the temperature file and let's see. So now you need to make sure that the dimensions are reflecting of temperature. So your first one is mass. The second one is length, which is in meters. And then you have time and temperature. So everything has to be 0, 0, 0, and the temperature has to be 1 Kelvin. Kelvin. The fourth one. Yep. Make it 1. And then your object is now capital T. It's no longer P, but it is a volumetric scalar field. So you have that. Now you can begin, come down your internal. You can begin your temperature by saying it is uniformly distributed in 273 Kelvin. You can start with 273, which is 0 degrees or so. No. Yes. Not uniformly, it's uniform. 273. That's it. And so everything else will remain the same. Do you get it? Exit.
Yes, please.
Exit. Control X. Yes. Y. Enter. Okay. So now, let's go into the control deck. The FV solution. Go to system and let's see. No. CD dot dot. LS. No, LS. LS, list, and let's see what you have in there. Okay, so here, your mesh is not going to be changing, right? But then your solution may be changing. Let's see the control deck, and let's see every schemes, and let's see every solutions. So open each of them and let's see.
So CD or Nano?
Okay, so Nano. So for files, you are using an editor for it. Directory, you are only changing directory, CD. Please read the document I sent and practice. Go ahead. Okay. Enter.
Okay.
So you can scroll down. You can see that here we have the application, IcoFoam, and all that. And so there is nothing here about any particular variable that you are interested in. So you don't have to change anything in the control dictionary. So exit. Exit. Now let's see FV schemes.
Is that FV schemes?
Yes, finite volume schemes. Enter. Okay, so you can see the DDT term, DDT schemes. So that's the time derivative schemes. You are basically saying it's forward Euler. And then your gradient, the grad schemes that Mrs. Momadi taught you and you've probably seen earlier on, the grad schemes. So you are basically solving, the default is Gauss linear. And then for the gradient, pressure gradient, you are saying it's the same thing. You can do one more if you want to change for temperature. You can do the same thing for temperature as well, but let's just keep it this way. For now, we are not going to touch this today because this goes into the case for the final day. So you are looking at the divergence schemes as well. And you can see that the divergence is phi and u. We are basically solving the divergence for velocity to be Gauss linear. If you don't know it, you can put banana. It works. So you get options that actually work in this case. So that's the trick. If you don't know anything in there, put something, and then you get an error. And that error will tell you what it was expecting. Now, scroll down. Scroll down, let's see the other schemes. So SNS grad, it's just orthogonal. It's fine. So you can see that each of the terms there has to be discretized according to certain schemes, right? Each of the terms has to be discretized. And so the FV schemes basically tells OpenFOAM which schemes to use to discretize which term. So the time-dependent term has to be discretized in a certain way. And your divergence and your gradient terms have to be discretized in a certain way. So exit, and then let's go to FV solutions and see. Okay, so here it's telling you what type of solver. This is mainly for the linear system. After you've basically discretized your governing equations like your Navier-Stokes equation, your continuity equation, you need to solve a system of a matrix, a set of matrices. So how do you solve it? So there are different solvers in there for each term before you assemble it into. Hello?
Hi.
Yeah, so basically, these are the other options as well. But you may not even change most of the things here for the foreseeable future, right? So you can keep this here. If you don't know, you could change anything. Now the tolerance here, you may have to change your pressure tolerance. So your tolerance you are saying is for OpenFOAM to consider that your system, your solution has reached some particular accuracy, you are saying that the difference between the previous time step and the current time step should be less than 1 to the power -6 for pressure. And for the case of velocity, you are saying it should be less than 1 to the power -5. Otherwise, keep going until you get something that is less than that. So that is what those numbers define.
Okay.
Yes. So let's end it here today and let's pick up tomorrow. And so try to work on the PITS daily thing. Play around with the mesh. And then let's see. Tomorrow when you come, you show me what you've done. If you've encountered issues, let me know.
Dr.